So if you recall, every single time we talk about creating an interactive calculator, we always say that we assume users input in integers. In fact, all the values that we have used so far, mostly we are dealing with integers, okay? So here's an example where we create a very simple addition calculator where we ask user for 3 values, and we assume user always enter an integer. So after user enter a value, I typecast it immediately to int, okay? And then I do the sum by adding all these 3 values, okay? So let's try, for example, 1, 2, 3, and I get the sum is 6, all right? Now, what if I want to extend it to floating numbers, okay? Now we can do so. So we allow user to enter decimal points, okay? When we enter the decimal points, now this time we want to do calculations involve decimal numbers. So we typecast this to float. All right, float support decimal points. So let's try it. Okay, suppose I say the first number that I want to enter is 0.1, and then it's 0.1, and then 0.1 again. Now this time, what I get is this sum here. Now, mathematically, the sum of 0.1 3 times, it should be 0.3. However, the calculator that we just created give me 0.3000004. It's not exactly 0.3, but something close to 0.3. So what we have here is that our calculator is imprecise. It doesn't give us the right value. It doesn't give us the mathematical correct values of 0.1 plus 0.1 plus 0.1. So is there something wrong with our calculator? Is it because our addition is wrong? What do we need to do about it? Okay, so this is what we want to study for today. Why? For integers, we have no arrows. 3 plus 2 plus 1 give us 6. This is exactly how the mathematics works. 1 plus 2 plus 3 is 6. However, when I do 0.1 plus 0.1 plus 0.1, the same calculation of adding them give me arrow. Give me a small arrows of something 0. Some number of zeros and 4 at the end. It doesn't give me exactly 0.3. Now, to understand this, we need to understand how numbers are being represented, okay? So everything in computer are represented using binary forms. That is either 0 and 1. So numbers, for example, integer, is also represented as a string of 0 and 1s. So we want to understand how this is represented. And then we proceed to understand how 0.1 is represented as a string of 0 and 1s, and why it can't be represented precisely, and hence give us a rounding off error, okay? So let's look at this. We want to represent integers, all right, as string of 0 1s. So let's look at base 10 decimal representations. This is how we use every day, where 2053 is basically represented as what we call base 10, okay? So it is 2053, all right? And each of them is multiplied by some power of tens, okay? 2053 is equals to 3 times 10 to the power 0 plus 5 times 10 to the power 1 plus 0 times 10 to the power 2 plus 2 times 10 to the power 3. Okay, so 2 times 10 to the power 3 plus 0 times 10 to the power 2 plus 5 times 10 to the power 1 plus 3 times 10 to the power 0 will give me 2053. So this is called base 10 representations. Every digit is multiplied by some power of tens, and you add them up, and this will give you the values that you are representing, okay, in base 10. So from left-hand side, the leftmost digit is multiplied by 10 to the power 0. The second leftmost digit is 10 to the power 1, followed by 10 to the power 2, 10 to the power 3. All right, now if you want to change to base 2, so base 2 is what the computer is using. Computer is not using, so when we type the number 2053, we interpret it as base 10, 2053. But when we store in the computer, it's stored in base 2. It has to be converted into 0 and 1s. Okay, this is how it's being stored, okay, in some zeros and 1s. So what is the base 2 representations? So it will be some 0 and 1s, okay? So base 2 means that it can only take digit 0 or 1. all right? And base 10, it can take digits from 0 to 9. So 0 to 1, how do we represent it? So how do we see in base 10? So 1 times 2 to the power 0, plus 0 times 2 to the power 1, plus 1 times 2 to the power 2, plus 1 times 2 to the power 3. So these are the representation. This is the binary representation. Everything is either 0 or 1. All right, if you want to convert it into base 10, you multiply by its sum power of 2 and then add them up. So what you get is 8 plus 4 plus 1 in base 10, and then is equals to 13. In other words, 13, how we interpret 13 as base 10 in computer is stored as 1101. Okay, so 13, when we type 13 in our computer here, when it's stored as 1101 because computers store everything in base 2. Okay, everything is binary. It's either 0 or 1. Okay, so the idea is the same. When you have a binary string, you take the leftmost digit, which is here 1 example, and 1 you will multiply by 2 to the power 0. And the second leftmost digit, whatever digit it is, you're going to multiply with 2 to the power 1, followed by 2 to the power 2, followed by 2 to the power 3. So each of these digits here will multiply by its respective power of 2, and then you add it up, and that's how you represent, how you convert binary representations to base 10. Okay, so we don't have to compute it ourselves. So in Python, there is a way to do it for you. For example, let's look at the previous example. We have 1101. So if you want to convert it into base 10, so you just make it as a string. So 1101. So this is a binary string. It contains only binary digits. All right. And if you want it to convert it into base 10, so what you're going to do is that you say that this is a binary digit. It's in base 2. And I want it to convert it to its base 10 int. So it becomes 13. Okay. Now, if I give you some numbers, integers, some integers say 13, how do I convert it into its binary representations? Okay, so we have this a function called bint. All right, you can put, for example, integer bint 13. So it takes a base 10 integer, okay, and converts it into a binary string. So it has some prefix called 0b. So you ignore these two elements. The rest of the elements will be the base 2 representation. This is how the computer will store it. So an integer 13 will be stored as 1101 in our computer. Okay, and if you want to convert a binary string to its integer, you use int with the string, say that this is a base 2 string, and then you want to convert it into int. Okay, so just to give you another example. So I say that this is an int in base 10. If I want to convert it, I want to see how it's being represented in computer as a binary string. So again, I do this 2053, and it gives me this. So 2053 in base 10, how we type it, when it's stored as binary string of this 100, a couple of zeros, and at the end we have 101. Okay, and again, you can also convert it back. So if you have a string, binary string like this, all right, which is in base 2 means it's binary, it's either 0 or 1. And if you want to know this string represent what integer in base 10, you just do int with a comma 2. And this is 2053. Okay, now we just say that everything in base 10 is from 0 to 9. Base 2, it will be 0 and 1. So are there any other base that we're looking at? There are base 3, they are base 16. Okay, so I'm going to put a remark. Just a quick remark. So base 2 takes only digits. So base 2 representation can only take 0 or 1 because it's base 2. All right, the digits can only be 0 or 1. Base 10 representations can only take 0, 1, 2, all the way to 9. Okay, so two numbers, base 2. 0 all the way to 9, there will be 10 numbers. So we start counting from 0, end at 9. So there will be 10 numbers. It's a base 10 representation. So we also have other base. You can also have base 3 representation. So base 3 means it can take 3 numbers starting from 0. So it will be 0, 1, 2. So your string can take 0, 1, or 2, but not 3 and 4 and 5 and so on. And then now, base 3 is less common. Okay, what is common in computer science is base 16 representations. It's called hexadecimal. Okay, so base 60 representation. So we need 16 numbers. All right, so we don't have 16 number. We have 0, 1, all the way to 9. That would be 10 numbers. All right, we need another 6 numbers. So we can't have 10, we can't have 1 0 as a digit. So digit is only one element. You can't have 2 element digits because, so if you have a string like this, so is this represent 10 or is it represent 1 and then 0? Which one is it? If you allow 10, is it 1 itself as a digit followed by a 0, or is it a whole digit 10 by itself? Okay, so we can't have 10 here. So instead, we represent the digit of 10 as an alphabet. For example, A, in this case, the standard version would be A, B, C, D, E, F. Okay, that will be 6 characters and 10 digits. That will be our base 16 representation in hexadecimal form. So base 16 is called hexadecimal. Base 12 is called binary. And base 10 is called decimal. And of course, base 3 is called ternary, and so on. Okay, so these are just some remarks, some things. You have seen hexadecimal. For example, in your HTML documents, the color encoding are in base 16 representations. Your IP address is also in hexadecimal representations. So the idea is that if you have, say, 10, so if you look at 10, being 10, so 10 is represented as 1010. Okay, as a binary, 10 is represented as 1010. So you will have a string 1010 as a binary string to represent 10. But 1010, you know, it's I don't want to have many, it's four digits here. 4 digits, okay? Instead, I can replace it by A. So it's just one alphabet. All right. So the idea is that if you have a long string, you might want to change it to base 16 representation, just like your IP address or your color encoding, so that you don't have a lot of zeros and ones. Rather, you can represent it as an alphabet where A represents 10, B represents 11, and so on. Okay. Now, so we'll talk about how integers are being represented as base 2 representation. Let's look at how 0.1 is represented as floating point number. Okay. Now, we're going to extend integer to floating point numbers, okay, where we accept decimals, all right, decimal points. All right, so base 10, the decimal representations, we have a dot here. Everything before the dot will be the same, okay? The leftmost digit before the dot will be those that are multiplied by some power of 10. We start off with 10 to the power 0, followed by 10 to the power 1. So 20 will be 2 times 10 to the power 1 plus 0 times 10 to the power 0. And then with a dot here, so you add some decimal points here. So these are the points that are less than 1. Okay, so we will multiply it by some power of 10 as well, but it's not a positive exponent anymore. It will be 10 to the power minus 1 and then 10 to the power minus 2. If there is a subsequent digit, this will be multiplied by 10 to the power minus 3. Okay, so 0.53 is represented by 5 times 10 to the power minus 1 plus 3 times 10 to the power minus 2. All right, so 20.53 can be written in this form, which is the sum of some digits, corresponding digit, multiplied by some power of 10. And how do we define this power of 10? Those that are before dot will be multiplied by 10 to the power some positive exponent, starting with 10 to the power 0, 10 to the power 1, and if there's anything more, will be 10 to the power 2, and so on. And after the dot, we will multiply by some power of 10 that is with exponent, negative exponent. So it will be 5 times 10 to the power minus 1, plus 3 times 10 to the power minus 2. And if there's another subsequent digit, we will have plus that digit times 10 to the power minus 3. Now we use the same formula for base 2 with very small changes. In base 2, our digits can either be 0 or 1. All right. And when we multiply by its corresponding powers, we are not multiplied by a power of 10 because it's base 2. We're going to multiply by some power of 2. Okay. So the idea is the same. Before the decimal, it will be 2 to the power 0, 2 to the power 1. And if there is a subsequent digit, it will be 2 to the power 2. After the decimal, it will be again, now will be minus 1. So it will be 2 to the power minus 1, 2 to the power minus 2. And if there is a subsequent digit, it will be multiplied by 2 to the power minus 3. So let's compute this. This is in the binary representation form. This is how the computer is stored. What does it represent? This is just a bunch of 0 and 1s. How do we know what is represented as an int? So we're going to do 1 times 2 to the power minus 2, plus 0 times 2 to the power minus 1, plus 1 times 2 to the power 0, plus 1 times 2 to the power 1. And what we get is 2 plus 0 plus 0.25, which is 2.25. So which means when we type 2.25 on our computer, it's being stored as 11.01 because in computer, everything is in base 2. All right. Now, then you ask, how about 0.1? How do we represent 0.1? So we use the same idea as before. So 0.1, 0.1 is less than 1, so we don't expect any integers here. If you have some, so all of these here must be 0. Otherwise, 2 to the power 0 is already 1. Okay, 0.1 is less than 1, so we know that we can't have zeros. We can't have any integer portions before the decimal. Okay, let's look at here. If we put 1 after the decimal, what it represents? It will be 1 times 2 to the power minus 1. So what does it mean? 1 times 2 to the power minus 1 means equals to 0.5. 2 to the power minus 1 means 1 over 2. It's equals to 0.5. Now 0.5 is more than 0.1. Okay, that's not what we want. We want to represent, so we want to find the binary representation of 0.1. Okay, this is what we are interested in for now, because just now, when we do the calculation, we realized that when we add 0.1 3 times, we didn't get a precise value, and we wanted to know why. Okay, so we wanted to know how 0.1 is being stored in computer. Okay, so we know that I can't put 0, I can't put 1 here, because if I put 1 here, I get 0.5, which is more than 0.1. So I know I have to make it 0. Okay, so the first digit after the decimal is 0, and then in subsequent digit, it can be 0 or 1. So if I put 1, I get 1 times 2 to the power minus 2, which is 1 over 4, which is 0.25. Now, 0.25 is again more than 0.1. So I know, okay, I can't put 0 here. I can't put 1 here, okay? It's going to give me more than 0.1. This is not what I want. Now, let's try more, okay? 0.1 here, all right? So this is a binary representation of now 1 over 8. Okay, so it will be 0 times 2 to the power minus 1, 0 times 2 to the power minus 2, plus 1 times 2 to the power minus 3. Now 2 to the power minus 3 is 1 over 8. Now 1 is 1 over 8, 0.125. Okay, this is again more than 0.1. So I know the third decimal points in terms of binary, it cannot be 1 as well. So we're going to continue this way. Okay, so we know all bunch of this has to be 0. If there are one of them that is 1, it will be more than 0.1. Remember, we want to represent 0.1. So let's go to the next digit. And this time, let's put it 1. If I put it 1, okay, what do I get here? So let's just put it 1 here. So let's add 1 more. 1 here. Now I do 2 to the power minus 2. 2 to the power minus 4. So the next digit, we're going to do 2 to the power minus 4. I couldn't copy it. Let's see. So we're going to do here 2 to the power minus 4. Okay, so we have 2 to the power minus 4 here. So I know that this has to be 0 because this is 1 over 8 as before, which is more than 0.1, which I don't want. So I'm going to set it to 0. And the next digit, if I set it to 1, I get 2 to the power 1 times 2 to the power minus 4, which is 1 over 16. And 1 over 16. So let's do a quick calculation here. 1 over 16 is equals to 0.0625. Okay, so which is 0.0625. Now, so if I set all 3 digits here zeros and then the 4 digits after the decimal 1, I get 0.0625. This 0.0625 is more than 0.1. Okay, that's good, which means that we just need to add more digits to the end so that it's closer and closer to 0.1. Okay, so this is less than 0.1, so we can keep this as 1. Okay, and then we know that it's not enough. 0.0625 is less than 0.1. We need to add more digits so that it become higher and higher and closer to 0.1. So we try the next digit with 1 as well. So now I have 1 times 2 to the power minus 4 plus 1 times 2 to the power minus 5. It will be 1 over 16 plus 1 over 32, and it gives me 0.09. Okay, this is good. So it increased from 0.06 to 0.09. It's still less than 0.1, but it's getting closer and closer to 0.1. Okay, now we know that it's still not enough. We want it to be closer, so we're going to add again. Now this time, if we add 1 here, 1 times 2 to the power minus 6, it becomes too much. Okay, so if I add 1 times, if I do 1 times 2 to the power minus 4 plus 1 times 2 to the power minus 5, if I add 1 here, 1 times 2 to the power minus 6, what I get is something that is much larger than 0.1. So I just give you a calculation here. So if I have 1 plus 16, 1 over 64. So 1 over 64 corresponds to 2 to the power minus 6. Okay, so what do we get here? We get 0.109375. This is more than 0.1. So we know we can't add 1 over 64. So that's why we can't put 1 here. It has to be 0. If we put 1 here, the sum of this will be more than 0.1. So I have to make it 0. Now the same thing, I try the next element. If I put 1 here, it's already more than 0.1. So I know I can't put 1 here. So it has to be 0. And then I add 2 to the power minus 8 instead. I put 1 here, means I'm going to add this number plus this number. What I get is something that is less than 0.1. So this is good. And then I continue to add, and it's still less than 0.1, which is 0.9960937.5. So this is getting closer and closer to 0.1, but still less than 0.1. All right, so we're going to continue this process again. If I continue to add, it will give me something more than 0.1. So I have to set it to 0. I have to set it 0. And then if I add 1 here, 1 times 2 to the power minus 12 is something that is less than 0.1. So I'm going to continue adding. All right. So in the end, I get something that is very, very close to 0.1, which is this number. So this number is 0.09997 something, which is still less than 0.1, but very, very close to 0.1 compared to all the previous numbers. All right. So what you can see here is a series of patterns here. You're going to start with 3 zeros here. Okay. And then 1, 1, and then 2 zeros, 1, 1, and then 2 zeros, 1, 1. So you can expect what's happened next will be 2 zeros again, 1, 1, 2 zeros again, 1, 1, 2 zeros again, and 1, 1, and this will go on forever. Okay, what you get is getting closer and closer to 0.1, but still less than 0.1. So ultimately, we have a binary representation that is infinite. We cannot get exactly 0.1, but we're getting closer and closer to 0.1. All right. In fact, we can show that it does not exist such a finite string for which it's exactly 0.1. We will be just repeating this pattern of 0, 0, 0, 1, 1, followed by 2 zeros, followed by 2 ones, followed by 2 0, followed by 2 1, all the way. Okay, so in most Pythons, there are 53 bits of precision available for floating point numbers. Okay, so 0.1 we store as binary representations. There is precise up to 53 bits. So each one of these is a bit. Okay, so it will represent it as 53 bits of this pattern here. Okay, so what it represents is a number that is very close to 0.1, but not exactly 0.1 itself. Okay, so this is why when we do additions of 0.1 plus 0.1 plus 0.1, we get something that is not exactly 0.3. Because in computer, when we type 0.1 in Python, 0.1 is represented as this at the binary string, which is not precise, which is not exactly 0.1. It's represented as something that is close to 0.1, 0.99999 something, and you went add it to another 0.999, add it again to another 0.999, you don't get 0.3 exactly, you get 0.3 with a bunch of zeros and then 4. This explains why our calculator, the one that we built here, is not precise. It's not because we calculate it wrongly or we program it wrongly. It's because when it's being represented, when the floating point number is being stored in computer, it's being stored as a binary digit, and 0.1 cannot be represented precisely as binary digit. It's represented as something close to 0.1. So when you add these numbers again and again, there is a rounding off error. Okay? So what if we really want exact arithmetic? And which number in particular? So before we come to the point where I want an exact calculator, I want a calculator like the one that I bought in store. I want to build that calculator that gives me exactly 0.3. How do we do that? Now, before we come to that point, you start to think, we know that integers is precise. Okay, integers, we have no issue. Our calculator will be precise. Now, floating point, there are numbers that will be not precise. But if we try different numbers, okay, let's try different numbers. Say 0.5. 0.5 and 0.5, as expected, it will give me 1.5. So not all floating point numbers give me imprecise calculations. 0.1 give me imprecise calculations, but 0.5 does not give me imprecise calculations here. It gives me precisely what I wanted. 0.5 times 3 is 1.5, exactly. All right, so there are numbers, there are decimal numbers that can be represented precisely. There are decimal numbers that cannot be represented precisely. Okay, so I'm going to write down here. Okay, so I'm going to write 0.1 when represented as binary form, as binary string, gives imprecise representations because it requires infinite many digits, in binary digits to represent it. And of course, we don't have that amount of memory, of infinite memory, okay? So hence, computations involving 0.1 might give rounding off error. So I put here might give. Okay, we'll come to that later. Why is that so? Because sometimes we get rounding off error, sometimes we don't. Okay, now 0.5 on the other hand, okay, so 0.15 as floating point number. All right, 0.5 in base 2 can be represented as finite binary representations. So it will be represented precisely. There will be no binary error. There will be no rounding of error because 0.5 is represented as 0.1 in base 2. So which we have seen before here. 0.5 is represented as 0.1 and the rest are zeros. Okay, because 1 times 2 to the power minus 1 is 0.5. So it can be represented precisely. Okay, so 0.5 can be represented precisely. Hence, no rounding off error. On the other hand, 0.1, it cannot be represented precisely. Okay, so hence 0.1 cannot be represented precisely. And results in computation involving 0.1 might give rounding off error. Now I say might because sometimes the errors get canceled out. Okay, so let's say we have 0.1 plus 0.1. It gives us 0.2. Hey, the error cancel out. All right, we didn't see a bunch of zeros with 4 that we have seen earlier. 0.1 cannot be represented as precisely, so 0.1 cannot be represented as precisely, but 0.1 plus 0.1 is represented as 0.2. But when we add one more 0.1, the rounding off error occur. Okay, with it's not precise anymore. And now let's look at if I add one more, rounding off error get cancelled. So this error can get cancelled out. So sometimes we get an error, sometimes we don't. All right, let's try it again. And now we get 0.5, it get cancelled again. But if we keep on adding, this error might appear again. Okay, 0.6, we are good. Let's continue and see 0.7, 0.8. So you do an experiment. Okay, so at 0.8, we get something that is again rounding off error. It's supposed to give us 0.8, but it gives us 0.799999, which is something close to 0.8, but not exactly 0.8. All right, so if you have a calculator that want to sum up these numbers here, it will give you an error. It will give you not a precise value, okay? And then you can continue to check. It'll get canceled out at some point, and then it can occur again at some point. Now it get a rounding off error continue to accumulate. And we will see that until this point, it should be 1. There are 10 of this 0.1 here. It should give you 1.0, but it doesn't give you 1.0. It gives you 0.999. Okay, and then you continue to find that some of them get canceled off, some of them did not get canceled off and result in rounding off error. So when we're doing floating point number, it's very tricky. We don't know when the rounding off error get canceled off. We don't know when it will occur again. So it's really depends on how it's being stored. It's because 0.1 can't be stored as a binary string. Now, now, what if we want to represent it precisely? Okay, what are the approach that we can do if we want to represent it precisely? Now, there are many approaches. In Python, for example, there are 2 libraries. One is called decimal and one is called fractions. And we will just look at decimal. Okay, so decimal is a library that will produce the same errors as calculation by hand. So if you represent your number, a floating point number, as a type of decimal, okay, then whatever calculation that you make will be the same calculations and mathematically correct. Okay, so how do we use this decimal library? So first we need to import the library. Okay, we need to import from decimal library. So this is the name of the library that we're going to import. And inside this library, okay, I'm going to use it. So if you want to import a library, you do import and the name of the library. Oh, sorry. The name of the library is small letter D. So you're going to import this decimal here. This is a library called decimal with a small case D. All right. So you're going to import this library and you want to find out what you can do with this library. There are a bunch of things that you can do with this library here. And you can go to the documentation to find out how you, what does this means here. Okay, each of them. Now we're gonna look at only one thing, which is called the decimal here. This is the only thing that we want to use, okay? So we're gonna import this capital decimal here. All right, and how we're going to use it is we're going to typecast, we look at it as a type. So decimal, so you can interpret capital D decimal as a type. Okay, instead of type float, now it's going to be type decimal with a capital D. Okay, now, so early on we say 0.1 cannot be represented precisely. So if we typecast it using string, okay, so we're gonna formulate it as 0.1 as a string, and then we put it into the bracket. Think of it like a typecast the string to decimal. So you can interpret it as typecast the string 0.1 as type decimal. Okay, so what you did is that you're going to store the 0.1 that you know will not be represented precisely if you type 0.1 itself. So you're going to encode it in the quotation mark as a string and then typecast it to decimal. Okay, you get a type that is of type decimal. So for example, I say D equals to this. Okay, and if I want to know the type of D, I get this is a decimal dot decimal. So this is of type decimal from the library decimal with a small case D here. Okay, so now, okay, if I put everything into this form, would I get a better calculations, where I get a precise calculations? So suppose I do this before I do this. So suppose I do this D plus D. So early on we say 0.1 plus 0.1 plus 0.1 does not give me the precise calculation. Now, if I typecast it into decimal, okay, so I have this here, decimal 0.1 plus decimal 0.1 plus decimal 0.1. What I get is decimal 0.3. Now, this is precise now. Okay, earlier on, 0.1 plus 0.1 plus 0.1 as int, as floating number, does not give me precise calculation. It gives me 0.3, a bunch of 0 and 4. Now, if I make them into decimal, okay, typecast it as string, put it as a string and typecast it into the decimal type and add them up, I get a precise value, which is 0.3, which is what we want. So decimal is a library that give precise calculations because they use a different way of computing it and also a different way of storing the values, okay? So this is how we can get precise definitions of calculation using 0.1. Okay, so now the question is, why not we use decimal all the time? So if decimal is going to give us all the precise calculations, why don't we just use it all the time? So because it's actually much slower. Okay, so CPU have floating point operation built in, but not arbitrary decimal precisions. So if you want to use a library decimal to change it into a precise calculations, it uses a different way of storing it, a different way of also computing it, which takes more computation times. So if you want to, for example, calculate how long it takes, what is the difference between using decimal or not using decimal, we're gonna run an experiment. Okay, so this is what we call a magic function. It's built into the Jupyter notebook that will give us the time it takes to compute these computations. Let's compare the time taken for each of these calculations here. So for example, I have A equals to 0.1. Now remember, A is of type float now. Okay, so A is of type float. We know it might give us, we know any computations. So any computation involving A, which is 0.1, might give us rounding off error, might give us error. Okay. Okay, and then we have b equals to 57. And we want to compute, for example, a over b. All right, we get this number here. All right, but we wanted to know how much time it takes to compute it. Okay, let's run it. So we say that, hey, it takes this amount of time, 9.3 milliseconds. Now, if we want it to be precise, we change everything into decimal. Okay, so again, I'm going to do from decimal, import decimal. Okay, now we change everything into typecast it into decimal. We can interpret as typecasting it. Okay, so it will be decimal 0.1 as a string, and b it can be decimal typecast it as 0.57, for example. And now let's do computations, a over b. So it's the same computation, except that now a and b here are of type decimal. Previously, a and b are of type float here. A over b is type float. And we're going to time it, how long it takes. All right. You can see that it takes 34.1 milliseconds on microsecond. So here you can see that when I do use the decimal, when I typecast it into decimal form, it takes longer time compared to when I just use float. Okay, so there is a trade-off here. If you want precise calculation, all right, then we have to trade off the time. It takes more time, but we can get it using the decimal library. But if time is of premium, its computational time is very important. If you want to do millions computations in 1 second, you can't afford to have expensive computation time, then we have to trade off with precision. We can say that, okay, it's fine that we have imprecise value. It's very close to the original value, to the value that we want. It's not exactly precise, but it's very close and it's way much faster. So it depends on your system, on your application. Is time is important? If time is important, we can trade off with some error, a little error. Okay, so that's how to represent it using decimal. Now, there are other ways of conversions besides decimals. We have fractions as well. Okay, and fractions is just, for example, 1 over 10 can be represented by fraction 1 over fraction 10. So we won't talk about this here. We will just talk about decimal here. And another thing that we can do is that 0.1 is not represented precisely, all right? But you can formulate it in a way so that it's represented precisely up to certain decimal points, all right, up to certain precisions. Now, we will talk more about this in the lab, where we can format it or round it into certain number of decisions, a certain number of decimals. Now, for now, let's use what we have learned before the end. Suppose we just want to have a precise calculator, okay? So assume user can enter numbers, can be floating point numbers. So we're gonna change all of these that we have here into decimal and give us a precise calculator. So it will be the same as before, except that instead of float now, I'm gonna change it to decimal. Okay, I'm gonna change it to decimal here. All right, so now I will have 0.1, 0.1, and 0.1, and my calculator now gives me 0.3. All right, so at the end of today's lecture, you learned that if you want a precise calculations and you allow user to enter floating point numbers, you typecast it into decimal and you get a precise calculation. But the trade-off is that when you do that, it takes a longer time to compute it. All right, so next we're gonna learn at what point you need to decide accuracy versus efficiency. All right, thank you, class.